So welcome everybody. Today we are here to listen to one of our graduate students, Ömer Faruk, Büyükkaya from the Mechanical Engineering Department of Yeditepe University. Could you project your...
Yeah, sure.
Ömer's master's thesis, he will defend his master's thesis today, and it is entitled Parameter Identification of Biphasic Hyperelastic Continuum Artery Models with or featuring a pullback algorithm. So we have approximately been studying this topic about 4.5 years, but he will explain the background. So the talk will last about 30 minutes. And then you will have question answer, and then you will stop our live streaming, and the jury will ask questions. So thank you for coming, thank you for being here, and I'm leaving the word to Ömer, so the floor is yours.
Thank you, Professor Fethi. Welcome, dear professors. Thank you for your being here. We started to work with Professor Fethi starting from my bachelor's degree, my graduation project, and this all started with working on some intervertebral disc modeling, and we converted it into a more general model that was an annular cylinder. Analysis of an annular cylinder in generalized plane strain and plane strain conditions. Then we connected with some other project. This was about muscular behavior, contractile behavior of a frog muscle. Then there was an idea. The artery is actually contracts in order to regulate the pressure developed within. So we connected with Professor Bilge, and we started to work together under a project under the vascular aging cost action. And this is the short story of ours. And now I want to continue with my defense. So my thesis title is Parameter Identification of Biphasic Hyperelastic Continuum Artery Model featuring the pullback algorithm. First, I will talk about the motivation behind this study and some basics of arterial mechanics. Then I will detail the theory of hyperelasticity and the material parameter identification scheme. Then I will present the verification and deployment of this scheme, and finally I will present some new results obtained from newly performed experiments. Growth, remodeling, and aging causes morphological changes in arterial body. These changes may lead to cardiovascular diseases. We are actually able to assess these mechanical changes, but we need some things. These are first, we need an experiment that mimics physiological function of artery in order to get a mechanical relationship with loading and response of it. And in order to properly model the material, we need a material model that includes morphological parameters along with the phase-specific material constants. And in order to obtain these constants properly, we need a powerful material parameter identification procedure. And this procedure should also account all states of the artery. The states of artery comes from the experiment performed, which is pressure myography. This also constitutes the configuration points in our formulation. When the artery is first excised, it's said to be in reference configuration. Then it is stretched with a constant extension ratio and mounted on a opposing cannula. It's in tethered state. When it is inflated with a constant pressure, it's in deformed configuration. Actually, this procedure can be assumed as an extension and inflation of a perfect cylinder, if artery assumed as an annular thick-walled cylinder. And this constant extension and inflation actually is an axisymmetric deformation, which takes place only in radial and axial directions. We can solve the radial mapping by imposing the incompressibility condition because of high water content of the artery. Actually, artery or in general biological tissue are not incompressible, but it can be assumed as so for practical purposes. If we equate the initial and final volumes of or reference and final volumes of the cylinder into each other, we can solve for the deformed radius R, which includes the only unknown inner radius, which is lowercase a. By the way, the reference configurations, the geometry of the reference configurations depicted with the capital letters, and the deformed configurations depicted by the lowercase letters. This convention is used throughout the formulation. In order to connect the loadings and the deformation that artery experiences, we need a material model, we need a stiffness. We prefer hyperelastic, biphasic, anisotropic, and incompressible material. In hyperelasticity, materials are defined with a so-called strain energy density functions, as seen here. For a biphasic material, for the matrix phase, we use the most known neo-Hawkian material, which depends on the only parameter, infinitesimal shear modulus mu. And for the fiber phase, we use Holzapfel-Gasser-Ogden model, which includes two parameters. K1 is the infinitesimal stiffness parameter, and K2 is the stiffening rate parameter. We connect these strain energy density functions into a more general one by using theory of mixtures, and we introduce a fiber volume ratio that represents the only one fiber, the volume, the ratio of one fiber family to the total volume. If we take a cut in the direction of fibers, one fiber family, we see a bunch of circles that packed in a plane. The fibers appears as circles, and the closest packing possible geometrically is actually 0.90, and for alpha parameter, 0.45 is the limiting number for us. And continue with the hyperelasticity, and starting from balance of energy, we use Helmholtz free specific energy to represent the energy within the material, which depends on the temperature and the formation gradient. We use index notation and Einstein's summation convention throughout the formulation. The gamma alpha represents the directional derivative with respect to reference configuration. If we assume isothermal conditions, the derivative of psi is equal to thermodynamic tensions, and the work done by these thermodynamic tensions is equal to the change in the strain energy density stored within the material per unit volume. And by taking the material derivative of it, we can arrive at the fact that W dot is equal to density times C dot. And the elastic part of the elastic stress power, where sigma ij is Cauchy's stress tensor and dij is the strain rate, this should be equal to time rate change of the strain energy density. And by using this, we can relate the thermodynamic tensions and the Cauchy stress tensor. And by using the relation between C and W, we can get a general definition for Cauchy stress tensor. Since left Cauchy green tensor is equal to F times F transpose, we define it as so. W is actually a function of deformation tensor. So this sigma ij, the derivative in the sigma ij can be expanded by using this dependency, and evaluating the derivatives, we can transform the sigma ij expression into this. For defining the deformation gradient, we take the deformation, we multiply the gradient operator from the left to the deformation vector. Since it is applied from the left, we write deformation gradient as F alpha I, and thus C will be equal to F times F transpose. In such an axisymmetric deformation, the deformation gradient is in actually diagonal form, and the components are the stretch ratios in their respective directions, and lambda z is imposed by the experiment. So in order to derive the stress components for an isotropic material, isotropic materials actually satisfies this equation, which means that under the coordinate transformation of the deformation tensor, the energy stored within the material should not be changed. Thus, we can a strain energy density function of an isotropic material is actually a function of the first three invariants of deformation tensor. By using this dependency, we further expand this sigma ij expression into a more explicit form, and by calculating these derivatives, we can get the most explicit version of sigma ij, or the contribution by matrix space. And this is written in the vectoral form for better comprehension. At this point, we take the Neuhuyken material model expression into the and inserting it into the AI coefficients. These comes from the derivatives of invariants, by the way. And this A1 coefficient is directly rendered as hydrostatic pressure P, which behaves as a Lagrange multiplier, which is an unknown to impose incompressibility condition, which will be solved during the solution. Then we get final components, matrix stress contributions. For the anisotropic part, we need to define a direction vector for the fibers. For the first family of fibers is represented The direction of them is represented by capital M. In the reference configuration, they are so aligned that they are wrapped around the z-axis and they are perpendicular to the r direction, the radial direction, and their alignment are measured from a plane normal to the z-axis. Here I4 represents the invariant in the direction of the vector. At this point we refer to Meredio and Ogden for this, and this is actually equal to the square of the stretch ratio in the direction of fibers. By using the dependency of W to I4, we expand the general definition of Cauchy stress tensor, and by evaluating the derivatives, we arrive at the contribution of the first family of fibers as shown here. For the second family, we follow a similar procedure. The only difference is in the direction, third component of the direction vector. However, it doesn't matter because the invariant is the square of the stretch ratio. This difference will be vanished, and it will be a similar expression for the stress components. By the way, this second family of fiber is perfectly symmetrical to the first one, and they are also wrapped around the cylinder embedded within the metric space. And having the expression, vectoral expression for the sigma or Cauchy stress, we put the Holzapfel-Gassner-Ogden material model into this equation, and evaluating then by using the theory of mixtures and adding these components of matrix and fiber phases contributions by multiplying with fiber volume ratio, we get the final explicit expressions for each Cauchy stress components. At this point, we insert them into the radial equation of equilibrium, and we get this equation by taking the integral of it from a to r. We get this expression. We are trying to solve for p of r and the hidden lowercase a, which is hidden in r, lambda r, or lambda theta as here. In order to solve P of A, we apply the boundary condition at the inner wall surface of the cylinder, which is the radial stress is evaluated at R equals to A is equal to minus Pi, which is the applied inner pressure, and we get the expression for P of A and insert into P of R. We get this expression, and then by applying the boundary condition at outer wall of the cylinder, we get a final equation that relates the applied inner pressure, axial extension ratio, and the deformation R, which consists of the unknown inner radius A. The only unknown is the lowercase a, which can be found by a root finding procedure. We actually try to we get the material constants by fitting this equation into the output of the material pressure myography experiment, which is pressure radius data. However, this fitting procedures have many issues within, because as we saw, The hyperelastic equations are very nonlinear, and the fitting equation is multiconvex, and we rely on a single input-output data, even it mimics the physiological function of the artery. These things can be cause overfitting, and it's seen that in the literature, most of the researchers are actually seen to be omitting or neglecting the tethering procedure, that is from excised to tethered state, because the measurement of an excised, radius measurement of an excised artery is really hard, if it is not impossible, especially for a smaller arteries such as mesenteric arteries. So they seem to be follow the direct optimization procedure or direct identification procedure following the path 1. However, we introduce a pullback algorithm that pulls back the artery from the tethered state to the excised state, and then continues with the path 2, taking the artery from excised state to the inflated states while optimizing the material parameters for the pressure radius data. So the scheme, the identification scheme is detailed here. It actually starts with the initialization by giving an initial guess. These guesses are very important since the hyperelastic functions are actually the hyperelastic material parameters are actually very sensitive to initial guess. Then the program evaluates the radial stress by using root finding for tethered radius and produces some calculations for the tethered state and compares it the experimental one. Then it pulls back the reference configuration, and it gives a guess about the geometry at the reference configuration or excised state. Then it takes these data to evaluate the radial stress by using root finding for pressurized radius, and it calculates the deformed or inflated radii, and it compares with the experimental data by applying a least squares, a nonlinear least squares algorithm. Then it is checked by if it is less than tolerance or not. If it is yes, it gives an output of the set of material parameters along with the unknown excised state geometry. For the verification, we apply the fitting procedure on a previously performed experiment, which is Simon's, and by using their definition of material, which is defined as the derivative of the strain energy density with respect to first invariant of the deformation tensor. They have two material parameters, which eta is the infinitesimal shear modulus and k is the stiffening parameter. I0 is just the I1 evaluated at the tethered state. They are trying to implement, they are trying to tolerate their because they are neglecting, they are started to fit the data starting from the first data point on the pressure radius graph. By omitting the tethering state, they measured the outer radii with respect to at different pressure points and calculated the inner radii from there. Thus, we fitted the outer radii with our formulation, and they actually derive their formulation with a thick-walled cylinder assumption. However, the fitting procedure was relying on a thin-walled cylinder assumption. In our formulation, we follow the similar procedure for the Hozafel similar to the Holzapfel-Gassner equation for this, and we get this expression that relates pressures and radii. And we get the output of our study, and the reported parameters are presented in this table. We get results that has a coefficient of determination higher than 0.99. When we compare the Simon with our direct method, since they are used the direct method, we again use the direct method, and there's the eta parameter is increased by 25%, and there is an 18% decrement in K parameter. This might be caused by the overfitting problem by assuming the thin walled cylinder, or by omitting the tethering state. And when we compare the reported parameters and the path 2 with the pullback algorithm, the both parameters are decreased drastically. More than a 50% and almost a 20% decrement is seen in parameters. And in fact, we get a less stiff material when compared to Simon's and PET1. Then the calculated radii are presented, including the exercise state, and it is seen that we get an accuracy that higher than 0.99%, and we are able to calculate all the radii. That means that we account all states, and we can recover the unknown exercise geometry when it is impossible to measure it, and we can produce more physiologically more realistic material parameters which are less stiff, and this shows us this identification scheme actually helps to avoid overfitting. Sorry. Next, we use Holzapfel-Gassner model along with the Neo-Hookean as a matrix material. We fitted this material model into again the Simon's experimental data. Alpha is taken as 0.25, having half fiber and half matrix phase within the material. So it is seen that for higher values of phi, it shows that increasing mu tolerates the insufficiency of axially leaned fibers to carry radial pressure, and lower K1s allows axial stretching for the fiber angles that are closer to the axial direction, and increasing K2 resists the shape change at elevated inflation pressures. Then by using these results, we perform the finite element analysis. The load is applied in two increments. In the first increment we applied the extension, and in the second increment we applied the pressure load by having a mesh such that we have 16 elements in radial and 96 elements in tangential direction. So the resulting mapping is presented here. Actually, we have three distinct arterial bodies, since we have fitted the experimental data by using different fiber angles that produces different cylinders at the beginning of the deformation. And here, by stretching the artery, this line shifts to the left, and in the second load increment, or by pressurizing them, these curves shift to the right. We see the same deformation under same loading, since we fitted the same experimental data, and it's seen that the cylinder with phi equals pi over 6 experiences the highest radial deformation. The reaction force versus load increment is given. This information can be useful for where the axial reaction force of an artery cannot be measured directly. And it's seen that larger fiber angles resulted in higher tethering reactions as expected, pointing to higher axial stiffness. And finally, the strain energy stored within the material is given. A momentary relaxation can be seen just after the tethering state for the cylinders with phi equals pi over 3 and pi over 4. And it is seen that higher fiber angles corresponds to a higher energy potential. And finally, I want to present results that are obtained newly. We fitted the Hozafels model again, our newly obtained experimental data. We have 7 number of individuals 10-week-old mice. We measured the radius. We measured the mesenteric arteries of them at 6 different pressure points, and in order to examine the change of the material parameters in case of the change in morphology of it, we seek a material parameter set at 9 combinations of alpha and phase. That means that we get a total of 72 parameter sets, and for a specific morphology, we compared them to 76-week-old mice. In this table, all the parameters that are obtained with a coefficient determination of higher than 0.99 are presented. As can be seen here, it gets harder to get a material parameter or to get a result that has than R square higher than 0.99. This might be caused by since alpha becomes closer to its theoretical or geometrical limit. And it is interesting to see that for higher fiber angles, it is also gets harder to get a material parameter set. On these results, by using these results, we performed an analysis of variance and student t-test of the material parameters of 10-week-old mouse mesenteric arteries for phi equals or fiber angle equals 30 degrees representing the first row, 45 in the second row, and 60 degrees in the third row. It's seen that as alpha increases, meaning the amount of fibers increases within the material, both of the fiber parameters are decreases, and matrix material stiffness increases. This is expected because the amount of fiber material increases within the embedded within the matrix phase. So then we again performed an analysis of variance on the material parameters of again the 10-week-old mouse mesenteric arteries. They are the same parameter as before. However, we at this time we kept constant alpha value instead of phi. In the first row, alpha is equal to 0.25, and in the second row, alpha is equal to 0.25. These plots are plotted versus these plots represents the material parameters plotted versus changing fiber angle, and it's seen that the infinitesimal shear modulus of the matrix material does not very responsive to the change of the fiber angles. And the infinitesimal stiffness of fibers decreases as the fiber angle increases, needing a less stiffness at the beginning of the deformation. And it needs higher stiffness values at the elevated pressures so that the K2 becomes larger as the fiber angle increases. Also, it's seen that K2 parameter is very sensitive to change in fiber angles. It actually shows a statistical significance in difference. However, we cannot see such a significance in other graphs. However, this doesn't mean that there is a practical difference. Actually, we can see some diverted data points, some diverged material parameters that are diverged from the average. These constants actually might be caused by the overfitting problems, since we are using a pressure radius data that are collected in 6 pressure points. By increasing these data points might be helpful to get a better fitting result. And finally, we have plotted, we again applied analysis of variance on the material parameters of 10-week-old mice at the first row and 76-week-old mice in the second row for alpha equals 0.25, and the material parameters are plotted versus increasing phi. And it is seen that K1 does not seem very responsive to the aging. However, mu, a significant stiffening behavior with aging is seen for the parameters of mu and K2. And it is seen that aging does not affect the trend of plots, meaning if K2, for example, K2 increases for higher fiber angles, it also increases for the elder individuals. So to conclude, the proposed augmented identification procedure has some upsides and downsides. It has actually the ability to find the unknown excised geometry, and it produces physiologically more realistic material parameters, which are less stiff than the found previously. And it helps to avoid overfitting by introducing one more equation for finding the excised radii. However, it is very hard to implement, and it is still sensitive to initial guess for all hyperelastic formulations. And overfitting is not disappeared; it is still an issue that goes on. This was all that I will talk about. Thank you for your participation and bearing with me, for your patience. And I want to thank Biphasic for this study, for realizing this study, and for supporting us. Thank you.